Good afternoon, everybody. In this video, we're going to talk about the linear expansion of a railroad track. You might have seen a video or pictures where the railroad segments are entirely deformed. Why it gets deformed? We'll be discussing about this one and how can we prevent this deformation. The short answer is of this deformation is because of the change in the length. And that's the reason there is some gap between each segment of the railroad track. If the expansion happens, then you provide enough space for the railroad segment to expand. If there is no gap between the segment, then it exerts a huge force on each other, and that force ultimately lead to the deformation of a railroad track. So let's calculate the change in the length and the force, how much force it exerts to the other segment due to the change in temperature. So to make life easier, we're just going to consider only one segment here. So we have one segment of a railroad track. The length of this one is 40 meter, which is given here. And we assume here the temperature to be minus 5 degrees Celsius. And all of a sudden, there is now, let's say, change in temperature. And the temperature now jumps from minus 5 degrees Celsius to 45 degrees Celsius. If the changes happens from minus 5 degrees Celsius to 45 degrees Celsius, what is the change in the length of the rod? For most of the materials, if we heat something, the length increases. Okay, so we need to find out what is the change in the length. And the change in the length or the increase in the length due to increase in temperature depends upon a parameter that is called the coefficient of linear expansion, that we denote by alpha. Okay, so here all the given parameters, the values are the length of the rod, which is the 40 meter, the initial temperature is minus 5 degrees Celsius, the final temperature is 45 degrees Celsius, so the change in the temperature is 50 degrees Celsius. The alpha, which is the coefficient of linear expansion, is given. All right, and the Young's modulus of the steel is also given. What is the Young's modulus measures is it measures the stiffness of the material. The equation for calculating the change in length is given by this equation here. And you notice here this change in length is directly proportional to the change in temperature and initial length of the rod. The more or the bigger the segment is, there will be more change in the length of the rod. Okay, so let's plug in all the values in this case. Alpha is given here, and this value is given for the material here is, I think this material is steel. This is for the steel material, it says here. So this value is for the steel, and it does changes with the different types of material. So 1.15 times 10 to the negative 5. The initial length is 40 meter, and the change in temperature is 50 degrees Celsius. So once we plug in all the values, the change in length, if we calculate, is 0.22 meter, 0.022 meter, which is 22 millimeter. What does this number tell you? This number tells you, like, if you design the railroad track, then there has to be at least 22 millimeter or more than, or 40 millimeter gap, 44 millimeter gap, because this might expand 22 millimeter, this might expand 22 millimeter. So there has to be at least 44 millimeter separation between each the segment. If it does not, let's say if there is not enough space, then what might happen is, let's say you have one rod here and then you have another segment here, if there is not enough space, then due to the change in temperature or due to the expansion, it might exert an enormous force onto each other. And due to this enormous force, these segments will be skewed or it will be deformed. And that's the reason, in order to avoid this deformation, there is always a gap between each segment of the track. All right. So now, I mean, and you can calculate for, like, let's say 50 degrees Celsius temperature or 60 degrees change in temperature, and there has to be at least double of the gap between the 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 the, railroad tracks. Now let's calculate the force, how much force it exerts, or how much force is required to make this change in the length, that we can calculate by the tensile stress. The tensile stress is the force, this force here, and divided by the unit area of the segment. So if you do this calculation, then the force per unit area, that we call the tensile stress, is given by this equation here. The Y is the Young's modulus of the material. Delta L is the change and L naught is the initial length. So the Young's modulus is given, we just calculated the change in the length, and this is the force per unit area or the tensile stress. Now let's say we know the cross-sectional area of the railroad segment or the track, and in this case the cross-sectional area of each segment is given here, which is 50 square centimeter. So if I just plug in now from this equation, if I calculate the force, how do we calculate? Force per unit area is given this number. So if I need to calculate a force, I need to multiply by the cross-sectional area. So this is what it is here. Cross-sectional area is given, which is this number here, 50 square centimeter. You have to change to the square meter. And the force is this value here, 5.5 times 10 to the 5 Newton. That means if the railroad tracks are just placed close to each other, and if there is not enough space, then they will exert a force equal to this number onto each other, which is equivalent to 62 tons of force. So it's a huge force, and due to this huge force, if there is not enough space between the two segments, then the tracks will be deformed. Okay, so this is the mathematical approach of calculating the force that can exert onto the one part can exert to the segment, and how much there will be the expansion of the railroad track. Again, if you have any questions, do not hesitate to contact me by email or writing your questions in the comment section below. Please like, share, and subscribe the channel. Thank you very much.